Hi, I'm Antonio Sala, and in this video we'll continue with the case study of designing a sequence of steps to achieve a given goal, which is moving a given system to a desired value in a desired time from a supposed experiment in which we could gather this blue curve. In this case, we will simulate a system with inertia, a second-order system actually. So we'll see that our computations that work perfectly in the first video of this case study do not work so well here. Computations in fact will be exactly the same, so the only difference will be the results. Let's go. The blue line will be our supposedly experimental data, in which I put a step of 1.25 in the input from an operating point of 2, and then I get a step response increment from an operating point of the output of 4 units that goes to 5.5 and has this blue line, and our goal is achieving a final value of 5.25, so we need a bit less power here, but we wish to achieve it in 1 second, so in order to climb up faster we will need a little bit of extra power in the first second, and then a little bit less of power so that the system stops going up. With it, if we assume the system is linear and time invariant, the only thing we need to do is a couple of proportionalities, so let's do it. Final value is 5.5, and the value at this point after 1 second in this experiment is 5.08. Good. If we wish to compute the equilibrium value of the input so that our desired value of 5.25 is reached, then basically our actual experimental measurement of increment of output is 1.5. The increment of input was 1.25, so the proportionality constant per unit input is this quotient 1.2. And now this is the increment of output I would have with a unit input magnitude, but if I want 1.25 then I need a little bit, in particular 1.25 divided by 1.2, which gives me 1.0417. Good. If I simulate that step, stepping from 2 to 3.0417, as the underlying system is linear, we get the correct final value with this step increment. If we now repeat the computations, but using this value here instead of the value in equilibrium, then we'll compute the step increment needed to reach our goal in this time. Indeed, the experimentally measured increment of output was 1.08, so if I divide by the experimental step amplitude, I get that if the step had been 1, the increment in 1 second would have been 0.86. As I wish 1.25 increment, then dividing this number by this number gets me 1.45 as the input needed to climb up to this value in 1 second. If I simulate that step, indeed we reach 5.25 in the required time. So the only remaining thing would be decreasing the power so that this is the equilibrium value. But as the system has inertia, when I simulate this two-step sequence, then the initial phase is okay, the equilibrium value is okay, but we have some overshoot. The system has some speed, the input acts directly on acceleration in this case, and this overshoot wasn't accounted for when I did my computations. But well, if this overshoot is somehow acceptable in practice, this may be a good solution, but okay, it's not as accurate as it was when we computed that thing with a different system which had no inertia, which was a first order one, and then the system instantly stopped at the desired value. But a system with inertia cannot instantly stop without, say, an infinite acceleration. This is what we are observing here. Of course, we could do some more complicated computations with models and whatever, but well, what we could do is just stop pushing before reaching the desired settling time to give time for the speed to dissipate because of friction or something like that. Let's see. I'm here putting in a switch factor of 1, so the time of switching to the second one will be the desired settling time with this switch factor. So I am simulating with a switching factor of 1. I am switching exactly at 1 second at the desired settling time, and we have this overshoot. But if I switch at 90% of the settling time, then I have this behavior. Well, I still have overshoot. I can switch at 60% of the target settling time, and then overshoot is mitigated, but I don't reach exactly the given value. So well, it's kind of a trade-off. The earlier I switch, the lower the overshoot, but the greater the error, in the sense that I won't reach the target value in the target time. So it's up to you to fine-tune this if you are happy with this strategy. Of course, there is a more complex strategy with a 3-step stuff in which you can sort of break here in order to modify these shapes. I am not explaining it here, it's just that the true way of fixing the value in a given time would involve something above the equilibrium to accelerate and below the equilibrium to brake when I am getting close to the target position. But of course, that complicates things, and it's out of the scope of what I try to explain here. So let us conclude. In this video, our idealistic goal was achieving this kind of response, in which for a given system, I specify a desired time and desired value so that the system reaches that value in that time, and then it keeps there forever. In a previous video, we achieved that with 2 steps in a system that had no inertia, but in here with a system that had inertia, so that at the initial phases it took some time to accelerate, and also at the final phases it takes some time to brake. Then applying the exact same computations, I indeed reached the target value in the target time, but then I had some overshoot because the, let's say, kinetic energy needed to dissipate before stopping. So the methodology in the previous video does not apply to all possible linear dynamic systems, but okay, it may be an approximately good enough solution in some applications. Moreover, if I know this fact of the inertia, so that I stop pushing before reaching the target position, then I get a trade-off between this overshoot and this lack of reaching the desired value at the exact instant I wish. In order to have a behavior like this one in systems with inertia, I will need extra push and some braking, let's say, i.e. a more complex input profile with 3 steps. But okay, those issues are not considered here for brevity and simplicity. So we finish the video here. Thanks for watching.